speaker is Sid Resnick, and you see the title of his talk, Sid.
It's nice to visit again, especially for an extreme value guy. It's nice to come during a once-in-30-year event, except if you come from Ithaca, nothing here seems so extreme in terms of the weather. I've worked with quite a few people on various bits and pieces of this. I'll probably forget to explicitly mention this as I go along, but this is my attempt at modesty. So. Now, session. This is a kind of vague, overworked term. Generally, the idea is it's some sort of higher order construct which you obtain by amalgamating more granular things. So maybe you amalgamate packets, or you amalgamate connections, or possibly you amalgamate groups of connections. But the feature here is that the amalgamation rule is some chosen, somewhat arbitrary rule. It's basically an algorithm that you teach to the computer, and it assembles your sessions from this rule. But the point that I want to emphasize is that it is not carved in stone. It didn't come down from Mount Sinai with the tablets. The point of doing this is that you're looking for some sort of Poisson structure to bring order into this mess of data. And once you have assembled the granular entities into sessions, you're looking for the distributional description of these sessions. So that's really the goal here. And you hope that you're going to find Poisson structure, and you hope that the sessions will be independent. Now the issue when you proceed is, what hat are you wearing? Are you the mathematics guy, or are you the empirical guy? So I decided today I'd be both. The mathematics, what you do is you take these sessions, you superimpose them, and there's this total input resulting from the sessions in 0 to t. So you imagine more or less you're pouring water now into a dam or into a receptacle, and the sessions are what you're pouring, and A of t is the total amount of work you've put into the system in 0 to t. And there was a lot of effort put into constructing limit theorems to try and understand the asymptotic behavior of this quantity. There were two kinds of limits. The type of limit that was most common in the probability community was what I call large-scale limits. It's where you scale everything up by t. So you have a fixed interval and you blow it up, and now it's a big interval. And you look at what happens in that interval. The other type of limit, which actually more faithfully reproduces the empirical experiments that people had done in the mid-90s, is what I call small-scale limits. You take time, you chop it up into small intervals, you scale each interval by delta, and you're going to let delta go to 0. So it's a kind of high-frequency limit in this case. So I'll just briefly outline what's been done in this section. And then if you're the empiricist or the statistician, you're going to actually collect packets. Well, in this case, it's packets. And you're going to take some rule, amalgamate these packets into a session, and use heavy tail analysis to get the statistical characteristics. And then you're going to search for Poisson time points among the assembled sessions. What is heavy tail? I am heavy tail. What do you mean? Heavy does not mean sub-exponential. It means Pareto-ish. Okay? So log normal to me is heavier than exponential, but it's not heavy. Is that all right? All right, very heavy. Wrong button again. There we go. Now, the modeling approach. How do we proceed with the mathematical modeling? So we're going to assume that sessions, however you've defined them, but sessions arrive according to a Poisson process. And the methods that I use revolve around decomposition methods, which really do need the Poisson property. But there is no doubt plenty of robustness here, and I think this is more a function of the methodology than of any intrinsic need. But we're assuming that sessions arrive according to a Poisson process. The parameter you have to remember is lambda. Lambda is the Poisson rate. And later on we're going to diddle with this lambda and make it move around. But lambda is the Poisson rate. And then we're going to assume that I've characterized the statistics of the sessions with three objects, S for size, D for duration, and R for average rate. And they are related. The average rate is the size divided by the duration. So obviously, to specify the distribution here, I have to specify 2 out of the 3 quantities. And then we amalgamate this to get the total inputted work. And in the small time scale approximations, we're going to let the delta go to 0. In order to get a limit, if you let delta go to 0, you have to assume the Poisson rate increases. Otherwise, you wouldn't get any limits. In the large time scale, then I'm going to look for a process limit in little t as the scaling factor capital T goes to infinity. And in each case, we'll have to center and scale by functions which depend on the capital T. There's going to be 2 kinds of results. Let's go back a minute. 2 kinds of results are going to be what happens when, say, here delta goes to 0. The other kind of result is I'll fix delta and ask what happens to dependence as a function of k. So I've got these little intervals. If I take an interval here and an interval here, how are they dependent? And it's going to be a little tricky measuring this, but in one case it's relatively easy, in the other we can do it, but it's open to interpretation. The message is going to be here that the type of results you get is dependent, very dependent on the distributional assumptions you make. And that's one reason why it's important to get the statistics right, because the approximations change fairly dramatically if you change the assumptions. So this is the first difficulty. If you want to make mathematical assumptions, what are you going to assume about the distributional structure of size, duration, and rate? And you look for guidance to the empirical work, and you discover that there isn't any very clear guidance being offered. Part of the result is that the studies, they tend to analyze different types of data. Some of the sessions that they talk about are based on actually transmitting files. In other cases, it's response data. In other cases, they're looking at connections. Sometimes it's sessions composed of packets. So what you look at is going to affect this decision. What you're trying to model is going to affect this decision. People have also used different amalgamation rules, different segmentation rules, depending on their purposes. And then the last feature, which is probably not going to surprise anybody, is that different applications will have different statistical properties. So for instance, streaming media would not behave the same as web requests. So here's a kind of catalog of lists of possibilities for the distributional assumptions. In the data I look at, it appears that S and D are jointly heavy-tailed. So that's one assumption you could make. A related assumption, but not the same thing, is you could take R and S And there's something which has been emerging in the extreme value community called the conditional extreme value model. This is where you assume S is heavy-tailed, but the assumption on R is only that if you center and scale R, then conditional on S being large, this has a limit distribution. So the type of R conditional on S being large stabilizes to some distribution. That's a possibility, which I haven't looked at yet. Then you go to the kind of more standard probability assumptions. You assume 2 out of 3 of those descriptor variables are independent. You could assume S is independent of R. There's some data which seems to point in this direction. You could assume that duration and rate are independent. That'd be another possibility. And there's good reason for thinking that perhaps it would be sensible to look at a mixture of these two assumptions. This is because under various thresholding rules, above the threshold it may behave one way, below the threshold the data may behave the other way. And then you could say, well, it's undoubtedly true that you never find independence in real network data, so maybe I ought to think of some form of asymptotic independence. That would create problems for the analysis. You can do it. I've fiddled around with it, or I've had students fiddle around with this. It gets pretty technical, but you can do it, and then at the end of the day, you don't really know much more than if you assumed independence itself. The other issue here is nobody exactly agrees on what a good definition of asymptotic independence is. There's one definition in extreme value theory, which is fairly unintuitive to somebody outside the field. And there are other definitions related to mixing and so on that have been used. So these are all issues, but okay. Now, how realistic are these assumptions? I'm assuming sessions arrive according to Poisson. That's obviously a gross simplification. If you're dealing with connections, for instance, you know connections always cluster. You press a button and there's machine-initiated connections based on your action. So this is obviously too simple. That's going to be an issue down the road. The other issue is, of course, I'm assuming transmission rates are constant across the session, but we know those go up and down. And the other issue is that I'm really not dealing with a network. I'm only dealing with an input model. This is just end user behavior. This is what the end user is trying to send down the pipes. But if you're interested in protocol design, this seems to be useful studies. At least that's how I talk to myself to let me sleep at night. Now, I'm going to be assuming that these quantities are all heavy-tailed in the sense that they have Pareto-like tails. They could be a slowly varying function, but generally I'll tend to de-emphasize those. If slow variation exists in real life, the statistician is more or less screwed. So you'd have a tough time figuring out what was going on if a slowly varying function was really there. So people tend to, for various reasons, they tend to assume it's not there. But theoretically, this is the level that there's no real problems assuming this. So I've got quantities size, sorry, the L should be a D, duration and rate, and we've got the corresponding Pareto parameters here. It'll turn out in what I report on later that if you segment the data in various ways, you may not always have R heavy-tailed, but initially I'm going to assume that it's heavy-tailed. So here are some of the small time scale results. Now I'm going to start out, and I remember I had that laundry list of assumptions, so I'm just going to give you two contrasting results based on two different sets of assumptions. So the first assumption is that duration and rate, average rate, are independent. So a reminder that sessions are arriving according to a Poisson process. Each session has attached to it this mark. So the session arrival time has attached to it the mark the size, duration, rate descriptor. S has a distribution f sub s, R has a distribution f sub r. And because I'm assuming S and R are independent, I'm going to get the distribution of D using a result of Bryman's, which says what happens when you multiply independent random variables, one of which is heavy-tailed, one of which is light-tailed. You get a tail which looks like the heavy-tailed tail. All the alphas are assumed to be between 1 and 2 here, so you have finite means but infinite second moments, so no variance. And the Bryman result requires an assumption, basically a left tail. So because I've assumed that S and R are independent, I'm getting D as the ratio of S over R. And this is basically saying that 1 over R has a light enough tail that the tail of D is according to the tail of S. Now, if you don't assume this, you will get different results. But I haven't systematically looked into that. But this is definitely a spot where I'm making an assumption that would vary. And if you don't make this, the results will vary. All right, now I'm chopping time up into intervals of length delta, and then we're going to ask what's the inputted work in those time slots. The limiting procedure lets delta go to 0, and because delta goes to 0, the Poisson input rate goes to infinity. And it's going to go to infinity at just the right rate to give me a limit. The right rate here is you take the tail, f bar, of the rate variable at 1 over delta, multiply it by delta, and that's just the right choice of lambda to give you these limits. All right, then you look at the input in the kth interval, and we let delta goes to 0. That's one set of results, and then the other set of results is you fix delta, and we're going to ask for the covariance as a function of k in intervals separated by k time units. Now, this is the case where I can talk about a covariance because we're going to have finite second moments. Second case is where I make a different set of distributional assumptions.
Perhaps I missed the definition of A. Work input is, what does that mean?
Session arrives and it starts pouring water into the jar. You count the amount, you count the water poured in during the interval 0t. If the session arrived too early or too late, you don't count it. If it arrived a little bit early but then stays long enough, you count the part that came in 0 to t. You're giving me that blank look, which no lecturer ever loves to see.
So it's the total amount during that period of time?
Yes. Yeah, so there's superposition over the different sessions. They can arrive clumped up, they can arrive sparsely.
Amount of work.
Sorry?
Each session represents a certain amount of work.
Right.
You have sinks.
I just have an internet, or, a reservoir. Think of it that way. Sorry? No. No. I mean, you could make a workload model out of it, but that's not the intent here. Second model, second set of assumptions. Now, a different pair are independent, duration and rate. And same choice of the Poisson input, function of lambda. But now, D and R are the independent quantities, so D times R is determining the S. So the distribution of S is going to be determined by F sub D and F sub R. So the primary quantities here are the distributions of D and R. And in this case, you find that you're going to have heavier tails than the previous case for the amount of work in a small interval that's been put into the system. So in 0 to delta, what you put into the system is of the order of the tail of F sub R, which is Pareto-ish with an alpha between 1 and 2. Previously, it was lighter. It was bigger than 2. We'll see a comparison in a minute. But the reason this is here now is you don't have a second moment for A. So I can't talk about comparing dependence using covariances, because the covariances won't exist. The tails are too heavy in this model. So I can't use correlations for assessing decay of dependence. So in the heavy-tailed world, there's various proposals about what to do. None of them are really any good. Mine is as bad as all the others. But I use the EDM, which is the extremal dependence measure. If you don't know what it is, don't worry about it. But it is something which is supposed to have properties somewhat similar to covariance for measuring dependence. But the point is you can't use covariance here because the tails are too heavy. The second moments are infinite. Now here's a comparison of the two models, and the message here is that the assumptions critically matter on the results. It doesn't just wash away. So this column is where I assume S and R are independent. This column is where I assume D and R are independent. And based on the two independent quantities, I get the third by either division or multiplication. So first off, you can see that the tails are very different. In the first case, the tail of the cumulative input looks like a Pareto with parameter which is the sum of the two parameters. Now, each of the alphas was between 1 and 2, so if you add one of them, pushes it beyond 2. So we have finite variance, and you can talk about covariances. Because you can talk about covariances, then the question is, if I look at two intervals lagged by k, how fast is the dependence going down as measured by covariance? And the answer is it's looking like the complementary cumulative of the tail of S. So the 0 there means take the tail, integrate it, and then make it back into a probability distribution. Thirdly, what does the asymptotic distribution look like? Well, you're going to get a normal, and that seems nice because engineers that I talk to, they don't really believe in heavy tails. They want to know that traffic at a heavily loaded node is normally distributed. So that accords with intuition. The other model, well, that's where the two pairs that are independent, that's where the pair that's independent is D and R. Now the tails are heavier. They look like the tail of the R distribution, so they're Pareto with a parameter between 1 and 2. The dependence is controlled by the D distribution, so R is controlling the rate of decay, D is controlling the dependence decay. So this is for a fixed delta as k goes to infinity. And now what you find is that the limit as delta goes to 0 is a stable law. So it's heavy-tailed. So in one case, the approximation is normal. In the other case, the approximation is stable. So you get very different results depending on what you assume. And the problem is, as I say, the empirical results aren't kind of pointing you in a very clear direction. Now, large time scale modeling, let me just briefly outline this story. Again, we'll assume that sessions arrive according to Poisson process, rate lambda. Now I'm going to assume that the inputs are constant and equal to 1. So I've taken some of the randomness out of the model. You can put it back in, and I've dabbled with some of this. I think the results are by now pretty complete, but these were the easiest ones to write down. I just did it quickly. So the randomness here is not in the R, which is assumed to be 1, but the size of the session is equal to the duration, because I've assumed the rate is 1. All right, now, what's the total input rate into the system? Well, the total input rate into the system is the number of sessions which are active at time t. Because at time t, the number of sessions active, each guy is pumping out stuff at unit rate. So the total rate is the total number of sessions that are busy pumping. What makes a session active? Well, the kth session is active if it arrives before t and it ends after t. So then your input rate at time t is just the total number of active sessions. So that's easy. And then the cumulative input becomes the integral of the rate. All right, and I'm assuming that session durations or session sizes is independent of the arrival times. So as before, I'm assuming that I've got a heavy tail here, Pareto type tail. The alpha is between 1 and 2. The variance is infinite, but the mean is finite. And a critical quantity here is what's called the quantile function b of t. And this b of t is going to be the 1 minus 1 over tth quantile of the distribution function, f sub d. It's written a little bit oddly, but this is so that I never have to write an inverse of a decreasing function. Decreasing functions confuse the hell out of me, so this is how I avoid it. All right, anyway, this b of t, because it's the inverse of an increasing function, which is regularly varying, b of t is also regularly varying, and its index is going to be 1 over alpha. And now, as before, I'm assuming that I have a family of models, in this case indexed by t, before it was indexed by delta. I have a family of models. In the tth model, my Poisson rate is lambda of t, so lambda is always depending on t now, and before it depended on delta. And in this tth model, I have an input process, I have a number of active sources process, and we're looking for a limit here. The limit is going to depend on the Poisson rate. So we're going to need growth conditions. And the rate parameter is going to be growing at a certain rate. We'll assume it's non-decreasing, and the asymptotic behavior of the input process is going to depend on whether slow growth or fast growth holds for this lambda. And here's the definition of slow growth. So I'm assuming, as before, that my session length distribution is regularly varying. So it's got a Pareto parameter between 1 and 2. And then what I'm going to fiddle with is the Poisson parameter, which is considered a function of this capital T. And then I'm going to have slow growth if one of the following 3 conditions, which are equivalent, holds. The first is in terms of the quantile function, and what you have to understand here is when I write lambda times t, lambda is a function of t also, so it's lambda parentheses t times t, okay? So that lambda is a function of t, it's just hidden in the notation. So this thing has to grow at a slower rate than t. The inverted form of this is in terms of the tail, it's f sub d, sorry, that L should be a d. F sub d of t, the tail probability, times lambda of t should go to 0. And the most intuitive way of saying this is in terms of the active source process. So m sub t of little t is the number of active sources at time t in the capital Tth model. And if over a time interval 0 to t, that dependence goes to 0, that's called slow growth. Fast growth is obtained by replacing 0 by infinity. So the other case that I'm going to consider here is where instead of seeing zeros on the right side, you see infinity. Okay? Slow growth, fast growth. And it's in terms of how the Poisson rate interacts with the tail of the distribution. That's what these conditions are doing. Now, the 2 results that you get here basically say that under slow growth, which would be the case, for instance, if the lambda were constant, under slow growth, the input process is asymptotically looking like a stable AV motion, and under fast growth, the input process, if you center and scale it in a different way, it's looking like fractional Brownian motion. So this was, these types of results were one of the justifications for this industry of limit results where you take fractional Brownian motion and input it into a cube. There were various models which said that under the right conditions, you would get fractional Brownian motion as a limit. And there's this relation of the self-similarity parameter to the alpha, which is fairly characteristic in this game. So again, the two types of limits you get, either stable wave motion or fractional Brownian motion. One's continuous, got Gaussian marginals. One's discontinuous, it's completely a jump function. And it's got stable marginals. So very different types of limits. Let's see. The boundary case has been resolved. The paper I like is Kai and Taku, but there's by now quite a literature on this in various cases. Okay. Now the empirical side of it. What do you learn if you look at packet headers? And how many of these assumptions seem sensible after you look at this? That's the question. So we're harvesting packet headers, and what you can get from these is source and destination IP addresses, port numbers, the size of the packet, the protocol, and when the packet rushed past the sensor. And based on this information, what are you going to do? So you'd like to assemble these packets now according to some rule and look for Poisson structure. Why do you look for Poisson structure? Because it gives some sense to the mathematical modeling, but also the internet results partly from human activity, and everybody believes humans behave like Poisson processes because we're all independent, right? So we need a rule for amalgamating these packets into higher order entities or sessions, and then we want to search for Poisson structure. Eventually we would like to be able to simulate all this, and hopefully the simulation model is an improvement on what exists. Now there was a paper coming out of Rice which studied burstiness, and we kind of used this as a starting point. They defined a session to be a group of packets which have the same source and destination addresses, such that they rush past the sensor with a threshold less than or equal to 2 seconds. The 2 seconds isn't that critical. I don't think the results are very sensitive to the choice of 2 seconds or anything close to it. But for instance, you're not looking at applications being the same here. You're not looking for port numbers being the same. You could do all of that as well, but it hasn't been done here. So this is kind of an overall traffic study. Again, you form your descriptors after you amalgamate into sessions. S is the number of bytes in the session. D is the duration. So it's the first packet compared with the time of the last packet in the session, and you can form the average rate. And gamma is, you think of as when you noted the time of the packet, the timestamp on the packet. We're going to look at some measure of peak rate later on. This was relevant for things like burstiness, so we'll see about that as well. So the idea is you start with these very granular discrete bits, and then you amalgamate them into something which you can think of as a continuous entity, this session. The data set we looked at, because of the Rice data. Now the people at Rice were very generous. They actually shared their data with us after it had been processed. They sent us this R file. We thought, great, we're really one leg up. There were some problems with what they sent us. Things like average rate exceeded peak rate. I don't know what well, we did eventually figure out what the source of the problem was. They were a little sloppy about some endpoint analysis, but we basically had to start over and download this from this website. The websites are also an issue because the websites go up and then they lose funding and they go down. So you've got to get them while you can. This one has been fairly stable, but there was something from Inliner which had this data on it for a while, and Inliner I think has lost its. That's an NSF-funded center. in the United States. It's lost its funding, and I think the site is by now down. It was supposed to stop operating last May. Anyway, this is 1 hour of data. That's the test for stationarity that we were talking about at lunch. You take an hour because you think if you take too long, it won't be stationary. It's TCP traffic and it's incoming traffic between 3 and 4 p.m. So we had roughly 1,100,000 packets. You apply the algorithm. If the packets arrive within 2 seconds of each other and have the same source and destination, they're part of the same session. And we round up with 44,000 sessions. This is supposed to convince you the data is bursty. This is just bytes per unit time. Time is running this way. Number of bytes per second is in the vertical axis, but I'm not going to deal with this. But this is why one might be interested in burstiness, obviously. Now, there was this quantity called the alpha-beta split. And what they did was the following. You have your session. And we have to change this. But you have your session. You pick a delta, small number. Chop the session up into intervals of length delta. And when you run out of things at the end, don't worry too much about it. And then you count the number of bytes in the subintervals. You take the maximum, and that's what they call the peak rate. And then they divided the group of sessions into 2 groups. The alpha group, the heavy users, these were the groups where you had a large peak rate, bigger than some threshold, say U, and the beta was everything else, where the maximum peak rate was relatively small. Okay, so power users have large peak rate, beta users are everybody else. And they looked at these 2 separately. Not surprisingly, they found that alpha sessions are the major source of burstiness. And then they pointed up a difference in the distributional structure of the 2 groups. So you've got 2 groups of sessions, and the distributional structure of that triple of descriptors seem different in the 2 groups. And that's really the main message that I want to leave here. In the alpha sessions, to them, it looked like R and S were independent. And I wrote sort of here because they measured this using correlation, and that's a very dangerous way to measure dependence in this type of environment. For the beta sessions, average rate and duration looked independent. So R and S looked sort of independent. Here, R and D looked sort of independent. So that was interesting. The other thing was that the beta group was huge. And we immediately wondered, well, why do you want to treat the beta group as one homogeneous group if you decided the whole data set was not homogeneous? Why treat this large group as homogeneous? Kind of iterate the argument. So you wonder if further segmentation of the beta group would give meaningful information. And we found actually the distributional structure varied when we divided it up further. And the question is, can you really make a model of that? So we split the data into M groups, where in our case M equals 10. So you don't want to make so many groups that you have no data to analyze. If you take 2 million data groups, you won't have enough data in each group to really say anything. So 10 seemed about the right compromise. And then how did we divide? Well, we composed the peak rate variable different from theirs, and we used the deciles of this miracle distribution. And based on that, we had 10 groups. So we're going to have 9 other groups corresponding to the beta group, and we'll find the distribution changes in these groups. And the point was that this was a very stimulating idea, but I think it masks further information. And probably something is going on here with conditional variables. So first, we needed a different definition of peak rate. So roughly now the idea is the following. We've got our session, and somewhere along the way you've got your packets arriving. Take k consecutive packets, look at the payload in that k, look at how long it took you to get that k, divide. That gives you an answer. Now you vary the k from left to right, take the maximum of those varying groups. So you look at k consecutive packets, start here and keep moving it along, like the scan statistic, which is a nightmare. Then you take the maximum of my k consecutive variables as I move from left to right, and then I take the maximum over k. And that's our definition of peak rate. It really is a peak rate, but the problem is if you had to work with it analytically, this would be a nightmare. Scan statistics are not fun. So that's the variable that we used for peak rate, and it turns out to have better properties. So we divided these 44,000 sessions that we originally harvested into 10 groups according to the empirical deciles of this peak rate variable. So we have 44,000 sessions, which means we have 44,000 peak rate variables, one for each session. And we can just write down the deciles and then segment the totality of sessions according to these percentiles. Within the groups, you can look at the distributions of S, D, and R and think about the dependence structure. Now, one interesting feature here is with this definition of peak rate, if you look within a decile group, the sessions seem to arrive, statistically, they arrive according to a Poisson process. The statistics look very good, conditional on the decile group. So this raises the point that you want to be conditioning on something. Not everything obviously is going to be Poisson, but if you condition on the value of some other variable, a covariate of some sort, you can get Poisson structure. Now, heavy tails means to me the tail looks Pareto-ish. Here, instead of an alpha, I've got a 1 over gamma. This is the extreme value notation. There's some reason for doing it this way here. So 1 over gamma is the old alpha. And the quick summary here is that the S and the D appear to be jointly heavy-tailed. For each decile group, they're jointly heavy-tailed, but the distribution seems to be definitely changing. The rate variable, now this is average rate, it's heavy-tailed only for the highest decile group, but not for the 9 lower decile groups. Now that's not really a surprise because if you are looking at a lower decile of peak rate, it seems to constrain the average rate. That seems perfectly reasonable. So the R is not going to be heavy-tailed for those 9 lower segments. What surprised us is R doesn't appear to be fit by any sort of distribution, even after you threshold it, any sort of distribution in a domain of attraction. So nothing in extreme value theory, no matter how you threshold this, seems to fit the R in the lower 9 decile groups. So that was a little strange, but that seems to be the case. To estimate the gamma, there's something called the Hill estimator. It's basically a maximum likelihood estimator for data over a threshold. So what you do is the following. You order, so this is a one-dimensional result. You order the data small to large. You take the k largest observations relative to the next one down the list. So I have k, I look at the one just to the left of the k. You average relative to that after you've taken a logarithm, and that's your gamma hat. Now, what's the point of the log here? The log converts something which is sort of Pareto into something that's sort of exponential. And then you're kind of doing what's the maximum likelihood estimate of a Pareto parameter? Of an exponential parameter, it's x bar. That's really all that's going on here. So the Hill estimator is one of those standard techniques which sort of works. It's asymptotically consistent if you assume something. Don't ask me what this is. I could tell you if I have to, but it's the sort of condition you would never know in practice. And you get a normality, asymptotic variance of gamma squared. But the point is, typically it's asymptotically normal, and you can use this asymptotic normality to get confidence intervals on the estimate. Now here's what these Hill plots look like. Now why am I getting a plot? You have here an estimator, but it's a function of the order statistics you chose. So basically you've made a choice of threshold. I'm going to use a certain order statistic, and above that as my threshold, I'm looking at the data. But I'm choosing a threshold. So what I'm doing in the next slide where I've got these plots is plotting the estimate as a function of this threshold or as a function of k. So this is for the 10th decile group, size, duration, and rate. The middle wiggly plot is a function of k. That's your Hill estimates of those gammas, size, duration, and rate. Those plots are pretty stable, so that's considered good plots. The band that's formed around them is the asymptotic confidence interval from the asymptotic normality statement. So that's what that looks like. So here is a table of these things. You have the gamma for the size variable, for the duration variable, standard errors from the asymptotic normality. And what you're supposed to see from this is that they vary, even if you take into account the confidence intervals. There's only one listed for the rate variable because only in the upper decile, the last decile, is the rate variable heavy-tailed. So it's really not applicable in any of these. So it appears that the marginal distributions vary by decile. And then the question is, what's the dependence structure? Now, the dependence structure is also going to vary by decile. In heavy tail analysis, there's something called the angular measure, and that's giving you a preference by direction. If you imagine a scatter plot of two-dimensional data, so I'm looking at S and D, two-dimensional data. A scatter plot is giving you directions where large values are likely to be. Now, what we're going to do to get this angular measure is the following. You have to first of all, standardize the pairs so that they have the same tail. They don't in practice. They have different alphas, different gammas. But we standardize. There's two ways to do it. One is a non-parametric method using ranks. The other is, imagine you just estimate the different tail parameters and then raise the two coordinates to the appropriate power to make sure they have the same power using the estimates. So, because if you don't standardize, then the big tail squashes the small tail. So you don't see any dependence. So we have to standardize. Then I've got these standardized variables in a scatter plot. I draw a big circle, and I look at the data that's outside my circle. And then I convert to polar coordinates, and I make a density plot only of the theta coordinate. So standardize, draw a big circle, retain the data outside the circle. Now I look at the thetas, and I make a density plot for the thetas. That's giving me preferred directions. Okay? This is basically a standard peaks over threshold method in 2 dimensions for assessing dependence. Now, this is a simple scatter plot for 2 deciles. I haven't done anything. I haven't processed the data at all. But the idea is to see that things differ. So this is S, this is D, and here I have the lowest peak rate decile, and here I have the 6th peak rate decile. And you can see here, just visually, things seem much more funneled than here, where the funnel is much broader. So it looks definitely different. This is what the density plots look like. So you remember, you standardize, threshold, convert to polar coordinates, make a density plot of the thetas. And this is the beta group, the lowest 9 amalgamated together. This is the alpha group. So the alpha group seems fairly flat as a density compared with the beta group. And this is the beta group decomposed now into the 9 lower deciles. And it's roughly seems to be flattening out. So this is lowest. This would be the 4th lowest, and then the 7th lowest. Sorry, 6th lowest. So it seems to be flattening out as we go from low to high. Now we'd like to relate the explicit level of peak rate to the dependence structure. So what I would love to do is, there's some parameter where I can parameterize a class of densities with that parameter, and the parameter could be somehow related to the decile group. This is what generalized linear models do. So let's look at that. My time is getting to the end. There's something called the logistic family, which has been used for this kind of thing. It's a one parameter family on 0, 1, family of densities on 0, 1. So if you, instead of 0 to pi over 2 for the theta, imagine it's just 0 to 1. This parameter is psi, and the family has the property that it's symmetric. For psi less than 0.5, the family is unimodal. And as psi goes to 0, you have perfect dependence. Perfect dependence means for the 2 coordinates, x equals x in distribution. It's concentrated on the diagonal. And for psi greater than 0.5, you get a bimodal distribution. And if you let psi go to 1, you get something called asymptotic independence. But this is asymptotic independence in the extreme value case. The limiting distribution concentrates at the extreme points, which means no 2 variables are large simultaneously. So here, everything looked roughly unimodal. Certainly no bimodal distribution. Well, other than that one, nothing looks very bimodal. So we did a we did a parametric fit for the 9 groups using this family, just maximum likelihood, and then superimposed the parametric fits over the non-parametric density estimates. It looks reasonably good. Of course, density estimation, especially non-parametric density estimation, is one of those black arts. But then what you'd really like is, if I give you the peak rate, what is the psi, which will generate the dependence structure for the thresholded data? And we found that a reasonable way to do this is with this generalized linear model, where the function of psi is the inverse of this g function, but it's linear in the log of the peak rate. This is empirical. I don't have any physical reason for this. The g function is one of the standard ones, except we put a half in there. The reason we put the half in there is because the data looks more or less symmetric, and that psi in 0 to a half was the region where we were getting the symmetric cases for that family. So this provided a reasonable fit, and you could get a simulation method out of this, which is possible, but the key here that I think is interesting is thinking in terms of the following. Peak rate may or may not be an actual covariate that you want to use. It seems promising based on this. But statistics sometimes looks like a black box. And I think what this points out, though, is that if you're thinking of traffic as being as approximated by some limiting process, probably what you ought to be doing is looking at some sort of mixture model where there's some mixing variable over some class of processes, and that's what's giving you the overall traffic. This seems to point very strongly in that direction. So. Let's see, let me just finish with some final thoughts. There are all kinds of consistency issues for different ways to model this. I mentioned this conditional extreme value modeling. It's not clear that if I know that S and D are jointly heavy-tailed, why this model should also hold. That's still a puzzle. We don't really understand this. I've segmented the data based on this peak rate variable. There's obviously lots of other ways to do this. If you have an army of willing graduate students, you might look into some of this. But an obvious way is to repeat this analysis, but after you've segmented first by application. And exactly how you use theoretically this idea of conditioning, I'm still thinking about. I haven't really gotten this under control. Our definition of peak rate's difficult to analyze mathematically, and one wonders if there isn't a better way to do this. But based on the traditions we were following, this seemed like an obvious thing to try. So that's where we are on this, and thank you for your attention.
Questions?
Can you, sorry, can you remind us how do you define the, how do you get the 10 deciles? How do you get the 10? So you keep looking at peak rate, peak rate, peak rate of each, or?
So you have your peak rate variable, and you take the empirical deciles of that, of those numbers. So
Why would you expect them to be identically distributed?
why would I expect what to be identically
I
distributed?
mean, those deciles. You're looking at 10 different things, peak rate, so, and then you compare them. You compare those 10 distributions.
Well, the session descriptors are not identically distributed. That was the point of all these slides.
No, I understand, but why would you have expected them to be, if you take IID data, you do that procedure, what would you see?
IID data for what?
You just generate IID data and you follow this procedure, peak rate.
So you're assuming that the peak rate variables have been generated by sampling from one distribution
No,
and an
I-
IID? What?
No, I'm just generating a sequence of IID data.
What's the data, though, that you
Any
generate?
data, any exponential.
You get the 10th order statistic, the 10% order statistic, the 20% order statistic.
Right, and then you compare the distributions of the peak, and then I follow the procedure with peak rate. Okay, I don't see it. So in other words, you are doing some type of subdivision based on peak rate. And
It's to get the groups to have roughly equal numbers of variables. You don't want the variables in each group to be so small that you can't do statistical analysis.
No, I'm not talking about the number 10. All I'm trying to say is I'm not understanding the reason why you would.
I need a rule which will put sufficient numbers of variables in each group that I can do some analysis, asymptotic analysis.
Right. Okay, we'll talk about it.
Other questions?
You mentioned in the convergence to the alpha stable V motion, convergence in finite dimensional distributions. I would have thought that by now somebody would have put convergence in M1 topology, at least in one dimension.
Oh, yes. One of the students I had did one of the cases in the M1 topology. The only problem is if you ask somebody, well, what do you think? This is in the M1 topology. They look at you and say, yeah, I remember there's something called the M1 topology. But it's not commonly used, so people don't know about it.
Problem it is used.
It works with the supremum functional.
And if you look at the multidimensional process, the M1 topology is pretty bad. And get too many continuous functions.
I think the case we looked at was where R was random, but lambda was fixed, and it converged from the M1.
Okay. Yeah, that's the case where you get
I don't know beyond that what happens.
I had a question myself. So, I mean, it seems that since TCP is considered here, is that if you have more sessions active at a given time, the rate would be reduced. So, which, if this assumption is okay, would mean that the assumption of independence of the triples SDR or SLR, I don't remember, might be challenged. Due to the fact that, say, if you have a bandwidth of B and you share it between at a given time between say n sessions, roughly in the good case it would be the rate that everybody gets would be divided by n. So, is there a way to assess the independence of the triples and the impact that this might have on this type of estimations? If they might be coupled by the R, by the rate, depending on how clustered these things are. So, I'm not sure my question is very clear, but so.
You're talking statistically.
Yeah, right. Because I mean, so these triples, if I get it correctly, you assume them independent of some kind, and
So conditional on the peak rate, yeah.
I see.
They were assumed independent.
And so, what would happen if one would take into account the fact that they might be coupled, or could one test the fact that they might be coupled by the fact that there is dependence between the R's of different flows, of different sessions?
I think that's really getting into this last point that I made, that I would like to think about how we condition on this, whatever the covariate is, if it's peak rate or something else, to understand the traffic as being conditional on a variable like that, which is providing the binding, giving you the dependence. Within a decile, I think things looked IID, but cross deciles, of course, not. I don't really know how to answer that in a more helpful way, but I think that is a key point.
Any other question? Okay, let's thank the speaker again.